Good morning, ladies and gentlemen. May I have your attention, please? Awesome. Raise your hand if you didn't get a red mark for today, the 5th. Is everybody good? Okay, so we're moving beyond our functions overview, where we took a little look at a lot of different kinds of functions in Unit 1, and now we're going to look at specific functions in more detail. And so Unit 2 is, as you guessed it from your reading questions, all about linear functions. So we're going to be taking a close at linear functions, how they can be modeled using different equation forms, how they can be applied to the real world, and it's a little bit shorter unit. So there's a lot of stuff in that Unit 1. It was fairly long. We made it all the way to October. Now our Unit 2 linear functions is a little bit shorter unit, okay? A little bit shorter unit where we're just going to take a more in-depth look at one category of functions as opposed to the 8 basic functions that we kind of developed in Unit 1. Awesome. All right, let's go ahead and take a look. So from page 149 in your text, the average BMI Y. So BMI, what does BMI stand for? What does BMI stand for, Adam? Yeah, body mass index. Y for a male of age X in years is given by the equation Y equals 0.07x plus 24.9. So we'll give the slope of the equation and tell us what it means in context of the problem. So be ready to share with the class what's the slope in that linear equation based on the equation. What's the slope there? Katie?
0.07.
0.07, good. 0.07. Thank you. And let's interpret that in the context of the problem. And so that always refers back to, right, in the situation, what does that 0.07 mean as a number in terms of the context of the situation? Margo?
How much the BMI goes up each month.
Absolutely. And so 0.07 represents how much the BMI, the body mass index for males, goes up each year that passes. Absolutely. Good. So the average male body mass index is increasing at a rate of 0.07 units per year, right? So if 1 year went by, we'd expect an average male's body mass index to go up by 0.07. Give the y-intercept of the graph. So what's the y-intercept if I were to plot this on the xy coordinate plane? Braden?
24.9.
24.9, thank you. In terms of the context of the situation, the 24.9 is not going to have the same meaning that the 0.07 does, right? The 24.9 would be the body mass index of a male aged 0 years. And we know that, right, when you're born, you're a little itty-bitty baby, your body mass, right? Your body mass may, I don't know that they have charts really established for infants. They have their own measurement systems to make sure that the babies are growing on track and so on and so forth. But I don't know that they have the established BMI that's the same, right, as for adults. And so this may or may not hold true in terms of the model versus the 0.07. All right, let's go ahead and take a look at a different situation that can be modeled with linear equations. Suppose the box office takes in $150 by selling X student tickets at $2 each and Y adult tickets at $6 each. Let's complete each ordered pair and tell what it means. And so the key here is being able to write an equation, right? That's what we call a linear combination. Anytime we have 2 or more things combining to give some predetermined total, and those are linear expressions, we can call that a linear combination. And so let's see. We're going to get that $150 by selling student tickets. That's one contributor. And by selling adult tickets. That's the other contributor. So together, right, if they're contributing towards some predetermined whole, that's a linear combination. So let's go ahead and see for every X, right, for every X student ticket we sell, that's going to contribute $2 towards my revenue. And so we could say 2X when combined with, how much does each Y adult ticket contribute towards my total revenue? Cody? $6, thank you. So 2x plus 6y together is going to equal our revenue that we brought in, and that was $150, right? So now we'll go ahead and consider some pairings that could produce that $150 revenue. If we were to sell zero for my X value, in this case, the student tickets, then how many adult tickets would we have to sold to get to our $150 revenue? So if we had 0 for our adult ticket sale, our student ticket sales rather, then we get no money from the student ticket sales, and all of our money, $150 revenue, would have to come from adults. So what did you get for the number of adult tickets sold then, if we sold 0 student? Taylor?
25.
25, raise your hand if you have the same as Taylor. 25 adult tickets, good, thanks, hands down, would have to be sold to get to $150. Thank you, versus if zero adult tickets had been sold, then they'd make no contribution towards my predetermined total of $150 revenue. All of that would have had to come from student ticket sales, right? Student ticket sales. So then how many student tickets would we have to sell then to make that happen, Eric?
75.
75, raise your hand if you have the same as Eric, 75, good job you guys. And then lastly, suppose we sold 15 student tickets. If we sold 15 student tickets, then right in there for X, we'd go ahead and put 15. And then we could solve for Y, bless you, to see how many adult tickets we'd have to have sold. So here we go, 15 in for X. We'll go ahead and distribute and get $30 plus 6Y equals $150. Subtract over the $30. So it looks like 6Y equals 120. And then divide by 6. It looks like we would have had to sell 20 adult tickets in order to still get my $150 predetermined revenue. So raise your hand if you have 20 for the last one. Can we have 20 for the last one? Awesome, you guys are doing great. Excellent. So when we can model the situation, right, by linear combinations, then you can see it's easy to find one coordinate when we substitute another value for the other, and that's what we're going to be doing today as we sketch quick graphs a little bit later with our standard form. Awesome. Okay, so ladies and gentlemen, let's go ahead and give yourself credit for assignment number 0. It was a whopper in terms of reading questions. Hopefully the assignment, though, from section 3.1 wasn't too bad. It kind of a review with slope-intercept form from linear equations, which is something you're familiar with. At this time, I ask that you make sure that your name, 1A, and number 0 are clearly labeled out top. If you give yourself credit for those that you completed out of 14 in pencil on the top of your page. Out of 14, divide, enter, multiply by 4. And then each reading question that you completed is worth a third of a point, so 0.3333. If you did 2 reading questions, then 0.6666 is what you'd add on to your book problem assignment score before rounding your final answer to the nearest half point, 0 to 5. So we're back up to 5 possible for your infinite canvas scores, and that's the first couple of assignments. Then we'll take a break from the reading questions and get back to them a little bit later. What questions do you guys have about your infinite canvas scores?
Wait, so if you did all 3, you added 1?
1. If you just did 2, though, so I know someone did 2 reading questions, then you add 0.666 before doing your final rounding. Because there's 3 reading questions, they're worth 1 total point. All right, let's go ahead and switch now from pencil. Everybody put your pencil down, let's get your grading pens, and we'll go ahead and grade your first assignment then from Unit 2. Okay, so we know our slope is m, our y-intercept is b in our traditional slope-intercept form, y equals mx plus b. Vertical, horizontal lines. 4a, the original volume of water in the pond. B, the rate at which the water can be safely drained. C, 10 acre-feet. 6 is 3, 7 is 1/2, 8. They've got undefined slopes. If we're talking about a vertical line that has undefined slope, we can't measure how quickly that line rises or falls as you move along from left to right because it's straight up vertical. Right? You can't move along from left to right, so our definition of slope doesn't make sense when we talk about vertical lines. We'll see that again today. Number 9, y is 2/3 x minus 3. Number 10, the slope's -2, the y-intercept is 5. 11, A, C, and E for the first part, and then B and D for the second part. 13, y is given by 0.03x plus 29.99. 0.03 is the slope, it's the constant rate per minute. And then y-intercept is the initial condition, or in this case, the monthly service fee. C, it costs $34.07. Number 15 is 1. And the final three, 16, the graph is shown, negative 2/3 x plus 4. You can see that positive y-intercept and then decreasing behavior as you move along from left to right because of the negative slope. 17, a horizontal line. Remember we saw that with our unit, our functions overview in unit 1. Y equals some number, y equals a constant like 5 is just a horizontal line. And lastly, 27, y is given by 48 minus 6x. This is an alternative form for slope-intercept form where we have a start value, some start value. Call it A, and then plus or minus bx, where b is our rate of change. So that can be a positive or negative rate of change. This is also slope-intercept form. It's just when you know some start value, maybe we call it A, and then plus the rate bx, your rate of change times x, is another way to write slope-intercept form. Awesome. So let's go ahead and make sure that you have your totals on top. Infinite campus score. Give yourself an accuracy fraction on a number you completed about how many did you get correct in pen. Circle that, please. The final check that's your name. If you need a stapler, sorry, I should have reminded you at the beginning. If you need a stapler, make sure you staple multiple pages together. That way they don't get lost and you'll still get credit for the hard work that you're completing out of class. If you need to go and do a stapler, that's great. Make sure you get it back to your column. And after you staple, go ahead and pass from the back to the front, please. Front rows, make sure they're facing the same direction. I appreciate your help. Pass them in. Everybody good with assignment number 0? Assignment number 0? Awesome. Thanks for your help with that, ladies and gentlemen. I appreciate it. And so, a little bit later, you're going to have an opportunity to work in partners today as we practice with our two forms of linear equations that we'll be looking at today. So, by the end of today's class period, you'll be able to determine the slope and intercepts of a line given an equation. So we're going to look at slope-intercept form and at standard form today. We'll recognize properties of linear functions. We'll model constant increase or constant decrease situations. We'll model linear combination situations. You already saw one with like the student ticket sales and the adult ticket sales together, combined to reach some predetermined whole. That's a linear combination situation. And then we'll graph and interpret graphs of linear equations. Specifically, today is all about using our slope-intercept form, our slope-intercept form, and our standard form of linear equations. And each of these has its utility. And so you might be thinking, why do we have more than one form for a linear equation? Is it just to make math more confusing? Is it just to make me not like math? No, on both accounts. We have multiple forms of linear equations because each one has their utility. Each one has their pros and cons. Sometimes slope-intercept form is the best form to use depending upon what you're trying to do. Sometimes standard form is easier to use depending upon what you're trying to do. And so we're giving you more tools. We're trying to empower you, not make math more confusing, but rather give you more tools in your bag, comma baby, so to speak, so that you can select and use those tools more appropriately based on what your task at hand is. All right, so let's go ahead and take a look at these. Our slope-intercept form then is y equals mx plus b on your note sheet. Y equals mx plus b, you probably recognize from middle school, or y equals a plus bx from algebra 1 is an alternate form for slope-intercept form. We just saw y equals a plus bx, is oftentimes used when we know a start value a and then the rate of change b. We could write it as y equals a plus bx, or the more traditional y equals mx plus b. Both are correct. Slope-intercept form is useful for graphing, if you're going to be graphing it. It's easy to plot the y-intercept on the y-axis and then count out your slope number from that point as a fraction rise over run to get additional points and connect them with the ruler. It's also useful for writing equations if you know the start value and the rate of change. So if you know the start value, that a, or the y-intercept b, and the rate of change, then it's a quick way to write a linear equation to model that. Standard form looks like ax plus by equals c. And so standard form looks like ax plus by equals c. In standard form, a, b, and c, as you know from your reading question, are all integers. And so they're integers. We typically choose a to be positive because it looks nicer. It's better math manners. And this form is useful when we're using a linear combination situation, right? If we have multiple things contributing towards some predetermined whole, then that's a linear combination situation. Some benefits of standard form is it's the best form to find the x-intercept of a graph or a linear equation. Another pro is that standard form can be used for any type of line. And so standard form can be used to write the equation of any type of line. And so that's useful as well. Go gadget arm for you in the back. And then point slope form we're going to look at next time. Point slope form is y minus y sub 1 is equal to m times quantity x minus x sub 1. And that's the quickest way to generate the equation of a line if you know 2 points on the line. Or if you know 1 point on the line and its slope already, then point slope form is the most efficient way to generate its linear equation. We'll deal with that next class. Okay, so your first reading question, right, was asking you to give the general formula for slope between 2 points and describe what slope means graphically, right? So our age-old formula back from Algebra 1, old school, going way back, with y sub 1s and y sub 2s and x sub 1s and x sub 2s, we can write the slope between 2 points simply by doing the difference between the y coordinates, call that y sub 2 minus y sub 1, all over the difference between the x coordinates. Call that x sub 2 minus x sub 1. You might remember hearing things like rise over run, where rise is how much your line rose or fell as you moved along it from the leftmost point to the rightmost point. Where that would be my run between. The left-right distance between the points would be called the run. The up-down distance between the points would be called the rise for the up-down distance. And my 2 points then would be x sub 1 comma y sub 1. And my second point would be x sub 2 comma y sub 2. We know that slope measures how much a line rises or falls as we move along it from left to right. And so this was from your reading question, right? You already had this spot in your reading question. So we didn't include it on your note sheet again. Slope measures how much a line rises or falls as you move along it from left to right. And this is key. Our definition of slope, right, hinges on moving along the line from left to right. Like we read a sentence from left to right. We measure slope as positive versus negative from left to right as well. So slope-intercept form looks like y equals mx plus b, where m is the slope of the line, or the rate of change between any 2 points. It measures the steepness and the direction of the line. We saw our formula before, m equals y sub 2 minus y sub 1, all over x sub 2 minus x sub 1. We can use slope-intercept form to determine if two lines are parallel or not. We can determine if the situation is constant increase or constant decrease, right? If we have a constant slope value. B is the y-intercept line, or the start value of the line. It determines if parallel lines are the same line. It's the starter value for data, right? When x equals 0, what's the y coordinate? That's the y-intercept. 0 comma b, where b is my y-intercept, or also called initial value. And we did include this on the printout, so you wouldn't have to write it all down, but these are some key informational things regarding slope-intercept form. Standard form looks a little bit different. In standard form, we're not solved for y, right? Not a formula, one variable alone on one side of the equation, rewritten in terms of other variables. Instead, standard form is ax plus by equals c. So we've added or subtracted to get all the x and y variables on one side, set equal to a constant. A, B, and C are not both, A and B are not both 0. A, B, and C are all integers, so no fractions allowed when we're in standard form. And then we'll make it so A is always positive. If after our work we get a negative A term, we'll just multiply everything on both sides by -1 to change it back to a positive A, because that's good math manners. Kind of like it was good math manners to list your domain values in increasing order, right? When we specified that last unit, it's good math manners to have A, that leading coefficient, a positive, just because it looks better. Awesome. Let's do some stuff. Let's do some stuff with it. So let's go ahead and rewrite the given equation in slope-intercept form. So right now, what I want you to do is find your example and decide which form this linear equation is currently in. Okay, so which form is this linear equation currently in? And be ready to share with the class when I call in. So which form is this linear equation currently in based on our two types? Go ahead and share with the class. Mark?
Standard form.
Standard form, excellent. This is already in standard form. Now let's go ahead and rewrite it in slope-intercept form. We said each has their utility. This is mainly just to get familiar with what the two forms look like. So in slope-intercept form, right, in slope-intercept form, we have it solved for y. Go ahead and share with the class what slope-intercept form looks like with letters when I call on you. So in general, what does slope-intercept form look like with letters, right? Caitlin? Thank you. Y equals mx plus b, where m is my slope of the line and b is my y-intercept. So we need to make that 4x plus 3y equals -7 look like this. Y equals mx plus b. So what are we going to do? Well, we'll simply solve for y in reorder. So we're going to get that y alone on one side. So we'll think back to our inverse operation. I know I can add or subtract, multiply or divide to get that variable y alone. So best first step, you guessed it, let's subtract 4x from both sides. Go ahead and bring down. And because I want to go make it look like mx plus b, I'm not going to put -7 minus 4x. I'm going to put -4x minus 7 so that I have my x term first, because I'm trying to make it look like that. I'll finish it out by dividing everything by 3, both sides. And recall when you divide that entire right side by 3, each term gets divided by the 3. And so if I want to make it look like y equals mx plus b, I'll have to split that up into 2 separate terms. Y will equal -4/3 x minus 7/3. So notice how we've now made it look like y equals mx plus b. Go ahead and pick out my slope m and my y-intercept b and be ready to share with the class. So if y equals -4/3 x minus 7/3, what's my slope n? My slope n. Aaron? -4/3. Thank you. That tells me how much my line rises or falls as I move along from left to right. If it's negative slope, guess what? My line falls as I move along from left to right. If you're math man or math woman and you jump down the left side of the graph, you'd slide down with your skateboard as you move along from left to right. In fact, you'd slide down 4 units, 4 y units for every 3 x units that you stepped over from left to right. So pretty steep. B, what's my y-intercept now that I've rearranged this? What's my y-intercept? Ben?
7/3.
Careful.
Oh, 7/3. -7.
Yeah, -7/3. That negative belongs to somebody, right? And it doesn't belong to the x term, so it's got to go with it. And that's important. And so thank you. That's absolutely right. -7/3. That's important because now we know that my start value is below the x-axis. I'm down beneath the origin for my start value on my y-axis. I'm at -7/3 for my start value. Awesome. I'll go ahead and box this to save for our notes. All right, so our second reading question then was to write y equals 2/5 x minus 3 in standard form. Remember that a, b, and c must be integers and a must be positive. So go ahead and tell the class then, right? Tell the class which form is this currently in, right? Y equals 2/5 x minus 3. What form is that currently in? Olivia? Slope-intercept form. Good, thank you. Slope-intercept form, it's easy to see the slope, 2/5, and the y-intercept, -3. Let's go ahead and rewrite this in standard form. In order to do that, we need to make it look like standard form, which is what with letters? So just letters only, everybody find standard form. What does the standard form look like with letters? Barrett?
Ax plus by equals c.
Thank you. Ax plus by equals c. So we're going to make this y equals 2/5 x minus 3 look like that. Ax plus by equals c, where a, b, and c are integers. Positive a. So what do? Well, if a, b, and c have to be integers, then we got to get rid of the fractions. So just like last unit, when you solved equations involving fractions, one thing we can do to clear the fractions in one fell swoop is multiply everything by the least common denominator. So if we multiply everything both sides by 5/1, we can clear the fractions in one fell swoop. So 5 times y is 5y equals 5 times 2/5 x is 2x minus 5 times 3 is 15. Check it out. In one step, we've gotten rid of the fractions. Hooray! Next, we want to add or subtract to get the x and the y term on the same side. Right now they're on opposite sides. We want them on the same side. So I would subtract 2x from both sides and put my x term first. So on the left, we'd get negative 2x plus 5y equals negative 15. And we're so close to being finished, but not yet. Recall that a, b, and c, right, are integers. Check. However, a should be positive. So what could I do to both sides to make a positive here? Right? What could I do to make a positive? Braden?
You can multiply by -1.
Good, thanks. So we're going to multiply everything by a -1. And that will change everybody's sign. So my final answer then will be positive 2x minus 5y equals positive 15. And now we're in standard form. So going back and forth between the two forms, right, isn't very useful in itself unless we need to do something with that line. It was mainly to get you familiar with the different forms, slope-intercept form versus standard form, and that's why I wanted to go back and forth. Olivia?
Instead of multiplying it by the -1, could you have just multiplied everything by -5?
Certainly. But you would have to see that the x would be negative at the end of the day. And so absolutely, that would have been fine. We can multiply by whatever we want so long as we do it to both sides and follow the golden rule. So absolutely right. Good. Other questions about your 3-2 reading question? All right, so let's go ahead and practice one then. We're going to go ahead and rewrite y equals 4x over 5 minus 7/2 in standard form. So Barrett told us that standard form looks like ax plus by equals c, where a, b, and c are all integers and a is positive. Right now, it looks like we're in slope-intercept form, so we need to get rid of those fractions, so a, b, and c are integers, and reorder so that we've got the x and y on the same side. This time, however, I have multiple fractions. So tell your partner what the best first step will be to do for this one, and be ready to share with the class. So what's the best first step going to be for this one? So what are we thinking, right? How can we get rid of those multiple fractions in the same problem? How can we get rid of those multiple fractions within the same problem? Tyler and Ben?
You would multiply by 10.
Good, thanks. We'll go ahead and multiply both sides by 10 every term, and that's going to get rid of the fractions in one fell swoop. So we're going to multiply everything by 10/1. That's both sides. So 10 times y is 10y equals 10 times 4/5 x is going to be 10 over 5 is 2 times 4x is 8x. You can take a minute and do that out if you like. 10 times 4x is 40x. 40x divided by 5 is 8x, right? If you want to do it top over bottom, that's fine. Minus 10 over 2 is 5 times 7 is 35. We can also do that out. 10 times 7 is 70. Divided by 2 is 35. Either way, this green line, no more fractions. No more F word, right? No more fractions. Now we've got a nice, easy equation to deal with. I want x's and y's on both sides. So I'm going to subtract the x term from both sides to move it over to the left. That gets me negative 8x plus 10y equals negative 35. And we're almost done, but not quite. How are we going to finish this out, Luke?
You times everything by -1.
Thank you. And so it looks like we need to multiply everything by a -1 to force that leading coefficient to be positive. 8x minus 10y equals positive 35. B and C can be negative. We don't care. We just want our A to be positive. So it looks like we've now got standard form. Awesome. What questions do you have about the second one? Moving and shaking. So let's go ahead and use our linear equations to do something then. So moving back and forth between the forms isn't useful. However, using the different forms, right, to sketch a graph or something like that, then would be useful. Please sketch a graph of the linear equation. Y equals negative 2/3 x plus 1. Be ready to share with the class when I call on you. What's the slope? What's the slope of that line given its linear equation? What's the slope of that? Logan? Negative 2/3, thank you. What's the y-intercept of that line given its equation? What's the y-intercept of that line? Brady? 1, thank you. The utility of slope-intercept form is that it's easy to sketch a graph if we're in slope-intercept form. So let's sketch that graph. Recall that we can plot our y-intercept on the y-axis. If my y-intercept was 1, I'll simply plot positive 1 on the y-axis as my start value, my y-intercept, and then I'll count up my fraction. I'll count up my fraction, my slope fraction, right? From that point, I'll go down 2 and over 3 to get additional points. That's my slope number. So I'll go from that point down 2 and over 3. Down 2 and over 3. I could even go backwards, so long as I was careful to then go up 2 and then backwards 3. And this way I can generate as many points on the line as I want. When I feel comfortable with that, we'll go ahead and connect those with the line then. So we've got our line. Pretty sweet. Are we good? Let's do another. Please sketch a graph of the linear equation. So if we're given slope-intercept form, it's easy to sketch a graph. In this case, I don't even have a slope m. I just have y equals negative 3. So this is one of our specials. One of our specials, we might recognize it from our parent functions last unit, y equals a constant k, y equals just some number. Think about what points would be on this line. What points satisfy this linear equation? That is, I need points on that line that have a y-coordinate of negative 3. So if I started to list some points, I might think, well, 0, negative 3 would be on there, but so would 1, negative 3, so would negative 7, comma, negative 3, or 10, comma, negative 3. This is the line that connects all the points who share the same y-coordinate, a y-coordinate negative 3. Let's think about what that would look like. So if I were to plot these, 0, negative 3, 1, negative 3, negative 7, negative 3, 10, negative 3, and connect them, this would form what kind of line? A horizontal line, connecting every single point that shared the same y-coordinate, the y-coordinate of negative 3. And so a linear equation that's y equals a constant is a horizontal line, and we saw that last unit. If slope measures how much a line rises or falls as I move along it from left to right, how many units does this line rise or fall as you move along it from left to right? Braden?
So the slope would be 0, so that would go up or down.
Absolutely. This line rises or falls 0 units as I move along from left to right. And so the slope of a horizontal line is always 0. And that's a key point. And so the slope of any horizontal line is 0. It doesn't matter if I was down 3 or up 17.7. If it's a horizontal line, its slope is 0. Consider the other special case when x equals a number. X equals a constant. This is the line that connects all points who share the same x-coordinate. And so one point on this line might be 4, comma 3. Another point might be 4, comma negative 6. Give me another point that could be on this line. What's another point that could be on this line? Eric?
4, comma 0.
4 comma 0. Thank you. Olivia? 4 comma 5. Thank you. We can continue listing points forever so long as the x-coordinate was always 4. The y-coordinate could be anything. It'll be on this line. So let's go ahead and plot those, you guys. 4, 3. 4, negative 6. 4, 0. 4, 5. And if we connect all these, we'd see a vertical line. So an x equals a number equation is a vertical line. Brayton told us that the slope of a horizontal line, right, the slope of a horizontal line is 0. As you move along it from left to right, we rise or fall 0 units. How many units do we rise or fall as we move along a vertical line from left to right? Well, can you move along a vertical line from left to right? If you're a math man or you're a math woman with that skateboard that you were using, right, and you bust the mad fat ollies as you slide down the negative 2/3 right slope line, are you sliding down this really, really fast, or are you going up it straight up, right? Slope doesn't make sense when you have a vertical line because you can't move along from left to right, and that was a key point of our definition. Therefore, the slope of a vertical line is undefined. It does not exist. And so the slope of a vertical line is undefined. It does not exist. There's no slope of a vertical line. Because we can't move along a vertical line from left to right. And our final reading question, I know some of you asked about that. Outline the steps needed to graph a line by finding the intercepts of an equation written in standard form. Then we'll compare those steps with the steps you would take to graph an equation in slope-intercept form. So these are key steps that we'll be using to sketch a quick graph using standard form rather. And that's one of the main uses of standard form is it's easy to sketch a quick graph using x and y intercepts. So how do we find the x-intercept? Simple. We plug in 0 for y and solve for x. Then we write our x-intercept as a point, x value comma 0. It's easy to find the y-intercept. We just perform the same process, right, in reverse. We plug in 0 for x now, solve for y, and write that as a point 0 comma y. The x-intercept occurs on the x-axis. And so any point on the x-axis has to have a y-coordinate of 0, and that's why this procedure works. We plug in 0 for y and solve for x to get an x-intercept. The y-intercept, right, lies on the y-axis, where all the points have x-coordinates of 0. And that's why this process works to find a y-intercept. So we force x to be 0, solve for y, and write our answer as a point 0 comma y. From standard form, we plot both intercepts and draw the line. From slope-intercept form, we only plot the y-intercept before counting out the slope number as a fraction rise over run and plotting additional points. Let's go ahead and try this process out and do something. So here we go. New equation. 6x plus a negative 4y equals 30. We're going to find the x-intercept and the y-intercept and sketch the graph of the following equation. Everybody. To find the x-intercept, it's easy in standard form. We'll go ahead and rewrite our equation, but we'll plug in 0 for y and solve for x. Let's do it. So I'll go ahead and plug in 0 for y and solve for x. So I'll rewrite. We'll plug in 0 for y. What happens to the y term in my equation when I plug in y for 0? 0 for y. It disappeared. It equals 0, so I'm left with the simple baby equation 6x equals 30. And now I can solve that through division. It looks like x equals 5. So my x-intercept in red would be 5, 0. Next, the y-intercept. Go ahead and rewrite the original equation, but now put 0 in for x and solve for y. After plugging 0 in for x, the x term disappears, and I'm left with the simple equation negative 4y equals 30. Dividing both sides by negative 4 gives me my y-intercept value. Y equals 30 divided by negative 4. That in turn equals 30 divided by negative 4 is given by 7.5. So I'm getting negative 7.5. So my y-intercept as a point in red would be 0, negative 7.5. Awesome. Let's go ahead and plot these and sketch a graph then. Here we go. The x-intercept was 5, 0, so I'll go on the x-axis and plot my point. There's my 5, 0. The y-intercept was 0, negative 7.5, so I'll go down on the y-axis, negative 7.5 units, and then we'll go ahead and connect them. That's pretty sweet. Let's do another. So I want you to go ahead and find the x-intercept by plugging in 0 for y and solving. Find the y-intercept by plugging in 0 for x and solving. Write each as a point, x, y, and then sketch a graph. I'm going to come around the room and see how you're doing. Catch my eye if you have a question. Okay, let's do a quick check. So x-intercept. I'll rewrite the original, but plug in 0 for y. What happens to the y term? It drops out, and I'm left with the baby equation 3x equals negative 15. Solving for x gives me x equals negative 5. So my y-intercept as a point would be negative 5, 0. Raise your hand if you have negative 5, 0 for the x-intercept. X-intercept, woohoo! Y-intercept, I'll gain in the same strategy, but this time I'll plug in 0 for x and solve for y. What happens to the x term after substituting in 0 for x? Disappears, and I'm left with the baby equation 5y equals negative 15. Solving for y gives me y equals negative 3, and we'll box my answer as a point 0, y, so I get 0, negative 3. Now it's time for a quick sketch. And so I've got my x-intercept, that's negative 5, 0. I've got my y-intercept, that's 0, negative 3. And so we're all ready for the graph. We'll go ahead and get a nice line. It's pretty sweet. Awesome. Raise your hand if you had the same graph. So who had that picture already? You had the picture already? Awesome work, you guys. Way to go. All right, so what we're going to do now is have an opportunity to practice. We're going to practice with our objective A and objective E is side 1 and side 2. So these linear equations now apply our slope-intercept form and standard form into real-life applications. We're going to go ahead and work on this with your partner. Okay, and when you're ready for a stamped eligible exercise, you're going to go ahead and come up to the front desk and check it with the key. And once you agree, you'll get your stamps. We're going to come back together for closure with about 5 minutes remaining. So you got a nice chunk of time. You get both your, if you get your stamps, and there's still time before 9:40, then you can go ahead and begin working on your assignment. We'll come back together for closure about 9:40, and I'll pause the recording now, and then turn it back on for closure. Thank you, ladies and gentlemen. Let's go ahead and take a look at our closure for today. So, think. On your paper, state the general equation for each form of a linear equation, then tell why it's useful. Okay, so we're going to write down slope-intercept form, the general form with just letters, and then I put a little star here. That's why the form is useful. So go ahead and write down what it looks like with letters, and then provide at least one situation where slope-intercept form is useful. Then go ahead and do the same for standard form. Again, write the general form with letters. And for the star, we'll go ahead and put one reason why it's useful. I'm going to go ahead and call on you to share with the whole class. So please be ready. Please look back as soon as you may. Okay, at this time I ask that you be ready to share with the class when I call on you. What does the general form for slope-intercept form look like with letters? So what does the general form look like with letters for slope-intercept form? Margot?
Y equals mx plus b.
Awesome, thank you. Y equals mx plus b, where m is my slope, and b is my y-intercept, my initial value, my start value. Excellent. And what is slope-intercept form useful? There's a couple things that slope-intercept form is useful. What's one thing it's useful for? Ben? Sorry. What's one thing that slope-intercept form is useful for?
Graphing.
Yeah, it's easy to graph when we're in slope-intercept form. It's easy to graph by hand. So it's easy to graph by plotting that y-intercept, that b value on the y-axis, and then counting out with your pen or pencil tip, right, your slope number rise over run to get additional points. Now, there's other reasons too. If you're given the initial value and the rate of change, then it's easiest to write a linear equation for that situation using slope-intercept form. Standard form, right, looks a little bit different. So what's standard form look like with letters? Caitlin?
C equals R A x.
Thank you. Where A, B, and C are integers, right, and A is going to be positive. And what's standard form useful for, right? What is standard form good for? Braden?
Finding the x-intercept.
Yeah, absolutely. Standard form is the easiest form to find the x-intercept form. And so it's easy to sketch quick graphs using x, y intercepts. I'm going to put easy to find intercepts. Or to model linear combination situations. Great job today, ladies and gentlemen. Come by if you have questions or concerns. Nice work.